recording. And all right, let me share the screen. Sure, I'm on the right screen. All right. Let me know if you don't see a VS Code panel and the browser on the left. Okay. And okay. And if you have any questions, like this, I want this to be more of a conversation, so that I know where, if you guys are following me. All right. So I guess on the Numba architecture, so a quick overview of that. First, I want to point out we have a very old paper, 2015, in the Numba organization that you can find. It talks about, it's kind of short, but it does talk about kind of a high level overview of what, how it goes from how the compiler works, essentially. It's not very long, so it's a quick read if it may help if you have other questions after this. The paper may talk about more specific things than what I would talk about here. But just for an overview. So what I plan to do is kind of using this code on the right, this really short compiled code. I'm going to step through it in the debugger and kind of show kind of the interesting parts. On the left is the, I guess it's a picture that we use. It's a kind of flow chart of how the compiler work. Everything going from like a Python function and then going through all the way to executable code at the end. And so I'll keep this on the left so that you can refer to it, and I will refer to it as we go. Start my debugger on this file. So hopefully at this point, everyone is already familiar with what this is. I mean, the code is very simple. I have a function foo x plus 1, and I decorated it. So as we start highlighting the key concepts, everything that is decorated Numba, they are a dispatcher. Just a second, someone just also joined it. So to those who just joined, we are recording this session. And I'm going through kind of the Numba architecture right now.
Okay. Yeah, fine with recording.
Okay. So, right, foo is a dispatcher. Everything wrapped in Numba is a dispatcher. And when we override the call, so if you step in it, you will, the first time you call it, it would ask for a new compilation. So that's why we landed in this method. The actual call is in some C code, so the debugger won't get into it, but the compiler is in Python code. So that's why we are getting in here. It's the dispatcher is asking to compile for the given arguments. So the argument is 1, and it would go through. I'm going to skip a lot of these. And call its internal compile method. Right. At this point is determined that the argument 1 is the int64, so it's requesting to compile for int64. We can step in. I'm going to skip to the interesting bits. So at this point, make this wider. The dispatcher handles things like this caching. So you actually would try to find, was this compiled before, recompile or compile if it's not existed. It tries to load from this cache, so it does this part. But if it's not there, it will eventually get into this line, which actually triggers the compiler. I'm just going to skip right through to the interesting bits. And then the entry of the actual compiler, almost everything ends up in this function, the compile extra. Step into it. Oh, there are a few things. All right. Okay, now we're in compile extra. Compile extra, as I said, is this the entry of the compiler. It takes a few important things. In Numba, we always talk about several contests. One of these is the typing contest. It provides all the information about types of stuff. Type inference will look up information about types in this contest. We have the target contest. This is regarding the kind of the back end, like what are we targeting? So here we're targeting the CPU, and it also contains like other compiler flags and also references to other compiled code. So it's managing Llvm cheat engine. So it contains all the executable code in this target contest for this target. So then we have the function, the argument types, the return type, which wasn't specified, so we don't know, and the compiler flags. Local is, for now, I'll skip it, something to work around typing. And then also skip library, and then we have pipeline class. This is kind of the driver for the compiler. It would have a sequence of passes in it. Yeah. Any questions so far? All right, I'll keep going. So here it actually initializes a pipeline class. And then the first step of compiling, kind of going back to here in the picture. So with a Python function, the next thing to do is to do a bytecode analysis. So now we are in the compiler. The first thing it does is actually do that, the extract bytecode. So the next thing is this class. Here we go. Let me quickly look into it. It's a function pass, and it calls into code from the bytecode module, number core bytecode. This file contains all the things to read bytecode. I'm gonna lose it. Okay. So this extracts the bytecode and it kind of prepares it in a form for further processing. It's because next thing we want to turn it into a number IR. So let me skip along. So now we have the bytecode, we pass it. So all the state is stored in this. Actually, now we are actually currently we're just building up a pipeline. So we are currently just adding passes to our pipeline to execute. So part of it is the compiler would define this pipeline from the compiler-defined pipelines. Since we're using the engine, it's using the no Python pipeline. It will end up here. If we can look into what's in there.
Can you explain what the no Python is versus
Right.
what is the other pipeline?
So Numba compiles code to not use, you compile code to not use the Python interpreter as much as possible. So that's why we say no Python is not relying on the Python interpreter once it is in the machine code. There are a few exceptions, like print. In Numba, to do a print, it actually asks the interpreter to print it for us. But for other compute-intensive parts, it doesn't use the interpreter at all. It's just machine code regenerate. The other one is the object mode. The object mode is kind of a fallback. It just asks the interpreter. It's like calling the CPython C API and to do all the operations. So you don't actually get any speed benefits if you use object mode, but it would support more things than no Python mode. I hope that answers it.
I was just going to say there's also the Cuda pipeline, which is almost the same as the no Python pipeline, but with a couple of passes removed. I can't remember what the difference is exactly, but you can compare them by looking at in number/cuda/compiler.py, there's the Cuda pipeline in there. If you compare that to where the no Python pipeline is declared, you'll see the difference. There's something that happens in no Python that's not needed for Cuda. I can't remember. There was a good reason I added it, but I've forgotten what it was.
I think it doesn't have, like, the CPU pipeline has some CPU specific optimizations. So the CUDA one would not use those.
Oh, I know. Does the CPU one actually send it through Llvm to JIT compile it? And we don't want that for CUDA. I think that's the difference.
Yeah. Yes. Yep. At the back. Yep. We'll go through some of the details on that now. So, right, we are here building up our no Python pipeline. So here you can see this method. It's kind of divided into three main sections: the untyped pipeline, the typed pipeline, and then the no Python lowering pipeline. Going back to the picture, the untyped pipeline is everything before type inference. So about this part, I think you can see my mouse cursor. The typed pipeline is type inference to rewrite IR. So all the kind of type inference and then doing everything that requires type, but before lowering. Lowering is when we generate the machine code. So the lowering pipeline starts from the lowering and all the way to something that we can execute. And look deeper into it. The untyped pipeline. So we start with translating bytecode. This is the bytecode analysis, and then we have the IR processing. So this kind of goes with the number IR generation. There are a few more things in between that's not shown in the picture. There were kind of things that were added, or optimizations added kind of after this picture was created. But all these are to do with kind of specific features, like with lifting, with is the syntax with context something. This kind of code that you have in Python, it is handled by this specific path. And then we have inlining calls. So actually, some inlining happens before we have type information. there's things like depth branch pruning, kind of other rewrites for different kind of features or optimizations. I'm going to skip some of these because there are additional details into the features that we support. And then it kind of ends with making sure the number IR is in SSA form. If you're familiar with compiler theory, this is the static single assignment form. Right. Back one, the typed pipeline. We have the type inference. The annotate types actually record information for debugging. And then we have passes to prepare or optimizations before the lowering. Here we all have more kind of inlining passes. And then we have the parallels. This is specific to the CPU targets for automatic parallelization passes. And then we go into the lowering. So now we are in kind of the lower part here. So lowering is this right here. So we kind of, this is this sanity check if the IR is same so far, the number IR. And then we lower. Lower is a very mechanical, mostly very mechanical, turning the number IR that we have so far into the Llvm IR. The NoPython backend is responsible for about this part. So it takes the Llvm, passes into Llvm just-in-time compiler to turn into machine code. It also generates a wrapper to call so that you can call the machine code from within Python. Any questions so far?
Why do you need the untyped pass?
The untyped passes, there are some passes kind of, I would say, the type inference cannot deal with all of the Python code. Some of the Python code needs to be kind of reshaped and pre-processed into a form that is easier for the type inference to digest. That's why we have the untyped passes.
So the untyped does some IR rewriting, or like is it before the IR step?
It's after, so it's in between. So we have the number IR, all the transformation number operates on the number IR. And yeah, so it's before type inference, it would transform them, rewrites them into a form to make it easier for type inference.
Okay, thank you.
And here I'm going to skip we already skipped the object mode. The object mode is very boring. You get bytecode, you get number IR, but you don't do type inference. It goes straight to lowering because everything is just Python objects, and there are basically not much optimization rewrite we can do. Right. So now that we define the pipeline, good. Jump out of this function. Oh, it actually is calling into the literal handling. I don't want to go in there. Okay. Yeah. Okay. I guess that's kind of a very high level overview. Let me jump back into to finish off the compilation. So this is going back into the dispatcher. So we were in here. Let me run it again. Stop at the right position. Yep. Okay. So at this point, we've completed the compilation, and we get this thing called compile result. And you see throughout the code base, it's called CREX. It contains kind of all these things regarding the compiled code. For the most interesting part would be first is the signature. This type signature here is basically what the type inferencer has inferred the function to do. It takes an in64, return in64. We call that our function is this x+1, and we're giving it a 1 as input. Inside the compile result, interesting things will be the library. The library lives inside here, the codegen.py file, which is the code library. This is where we kind of bundle all the Llvm IR together, and it kind of interfaces, you kind of use with this thing called JIT CPU codegen. The codegen is the class that manages the Llvm JIT engine. So here, this is part of the kind of setting up kind of target information for the JIT engine. Maybe more interesting things in the base class. So here is the engine. This JIT engine is referring to the Llvm. This class also contains the Llvm path managers. They are responsible for the optimization in the Llvm level. You can see there are kind of two sets. One for chip passes and one for kind of the full optimization passes. You see them being used later. Oop. Yep. So you can see they're being used in this optimized final module method under codegen. And there are many more details in how, as the code, once it's been loaded, it has to kind of, there's some kind of system loader like work to be done here, and linking modules, making sure that all the addresses are there and there are no undefined addresses, and fixing up recursive calls. Right, going back to this point. Now that our compiler returned this CREX, everything is already in memory, it's in the JIT engine. It calls this method on the dispatcher, add overload. All it does is basically remembering, storing that argument, that function signature, and corresponding to that compile result. And then in the C code, it would actually set up the call. Here, entry point is a Python callable object. It also contains a C pointer. So that once this is passed into the dispatcher in the C code, maybe we can quickly look at that. The underscore C.cpp is quite big. All right, I have to move fallback. This is a Cuda call. Yep. So when a dispatcher is called, this is what gets invoked, this C code. A lot of it is handling the arguments. And this part is doing a function lookup, seeing if the given types is available in this dispatcher. If there's no match and this compilation is enabled, it will try to compile. So it goes through something like compile and invoke. Otherwise, it will just call it. And then if we go to compile and invoke, this is how we get into the compile for arguments. You can ask for that method, calls it. And the CFA is the compiler call. Once it's done with the compilation, it gives this defunct. This is the callable. So we could say call defunct. A lot of this is setting up for tracing to work. So you see pi frame set up. Otherwise, this is calling this function with the given arguments. All right, that's kind of the life of a number compiled function. Any questions?
No, that was very helpful. Thank you.
When do you go to the C code? Like, or is that a simple example that doesn't go?
Where do you, so all the dispatcher object, so it's going back
Oh,
here.
the dispatcher is a C.
Yeah.
Oh, okay, I missed that. Thank you.
Yeah, the dispatcher object has not the entire thing is in C, but it has a base class that overrides the Thunder call, and that would get into this C code.
Mm-hmm.
Yep.
Thank you.
Yep. So you can see here is the TP call, is the dispatcher call. That's the Thunder call. All right. Any last call for questions regarding this kind of quick overview? All right. All right, I will stop recording now.